Okay, Algebra 2, this video lesson about chapter 10.4, Ellipses, follows up today's in-class lesson where most every student was in attendance. So the video lesson is primarily targeted at the very few students who weren't here today, and also to provide support as you prepare for the final exam review in a couple of weeks, in case anybody's forgotten how ellipses work 2 weeks from now. So let's get going. The first thing I'd suggest you do, and what I did in class, is show you a couple of YouTube videos. Here is the link to one, and you can probably look up your own YouTube video for, I typed in drawing an ellipse, I think, or sketching an ellipse, something like that. Came up with this, and this is a perfectly good example. If you plug this into your browser and watch it, you're going to see what the textbook talks about here in this diagram and in this paragraph statement, which is that if you have, instead of the center on a circle, if you have two different points, in the video that I just linked on the previous slide, these points are represented by toothpicks, and this blue two-part line is created by a piece of string. If you have two different anchor points and a piece of string, rubber band, whatever it is connecting them, the point they're making is if you stretch it to its maximum length and trace around, you're going to create a shape that's like an ellipse. And what you're also going to notice is that the length of these two pieces always have to stay the same. What you see if you watch it in that YouTube video is that it's actually a triangle here. This bottom piece of the string that runs between the two toothpicks never changes its length. In fact, the whole string never changes its length. It's just that it keeps adopting a different shape as you move it around the two toothpicks. So that's what the textbook is saying here when they say D1 and D2 stay constant. And if D1 and D2 stay constant, stretching out from these two anchor points, then the ellipse is all these points P that you're going to trace with that pen or that pencil. A couple of other vocabulary words that we talked about in class. We talked about vertices, major axis, co-vertices, minor axis. They're easier to follow if you look at these two diagrams. The one on the left shows what we called a horizontal ellipse. The one on the right, and it's a little bit rounder, I suppose, is, even though it's a little rounder, you can probably tell that it's stretched farther this way. It's a vertical ellipse. And so here are the key terms represented visually. The vertexes, in green here, are the end points of the longer side, the longer axis, or major axis as the textbook calls it. So here, vertically, this time, the vertexes are at top and bottom. These things called the co-vertexes are along the shorter sides, the minor axis, as it's called. And here they are again, the co-vertexes along that minor axis. For now, that's all I want you to follow from this diagram. I'm not going to worry about these words focus here. We'll come back to the focuses. But I do want to point this out. Let's see if I can quickly cover this up. Let's just look for now on the left here. If I had that, x squared plus y squared equals 1, that would actually be a circle. What causes you to have an ellipse is the fact that the x squared term and the y squared term are not in balance. And because they're not in balance, you're not pulling equally in the x direction and the y direction toward the center. You're pulling in two different amounts. And that creates some lopsidedness. That creates that ellipse effect. When you have a horizontal ellipse, that happens because the larger of these two numbers is under the x term. When you have a vertical ellipse, it happens because that larger number is under the y term. An example will make this make more sense, and we're going to come to that in 2 slides, so don't worry. But I just want to point out this green box before I forget. This is straight out of the textbook. And they're saying essentially the same thing that I just said, but you might want to make sure that you've at least looked at this from the textbook. They say the same two different equations and the same point when A In other words, the larger number is under the x term, it's horizontal. When a, the larger term, is under y, it's a vertical ellipse. That's all I'm going to talk about right now. Like I said, I'm going to come back to this discussion of the focuses, or as the textbook calls them, the foci. Now, as promised, here's that example. Well, one thing I'd forgotten to say on previous slides, for all of the rules that I'm about to teach you in this video lesson to work, this number has to be 1. Go back 1 slide, notice this was 1 in both cases. Go back 2 slides, and again, that's 1, that's 1. So in order to make this 1, you've got to divide 144 away. Divide everything by 144, in other words. You've then put the equation in what's called standard form. Okay, so dividing everything by 144, you end up with this. And I hope that makes sense. Hit the pause button. Whoops, if it doesn't, but can't get it to let go. But now you're in standard form. So ask yourself, is this going to be a horizontal or vertical ellipse? Well, it's going to be horizontal because the larger number is under the x squared term. That's what the textbook is saying here. It's going to be horizontal. Now, all of the examples that I'm going to be giving you in this video lesson and that I gave in today's class were where the center of the ellipse is at 0. So you move along the x-axis the square root of this number of spaces. So in other words, you move 4 spaces, and in this case, since it's the x-axis, 4 spaces right, 4 spaces left. That's what this is showing, and it makes these 2 points, -4 and 4. And then along the y-axis, you move, well, what's the square root of 9? 3. You move 3 spaces up and 3 spaces down. You hit or make those 4, I can't tell in this light whether they're all green or some are blue and some are green, but those 4 dots, and then you connect them and you've got your ellipse. The textbook goes on from here to talk about the foci, but I'm not going to talk about that yet. Instead, I'm going to ask you to work out this example, hit the pause button, and I do want you to, as the textbook says, graph, identify the vertices, identify the co-vertices. Don't worry about the foci. Hit the pause button. When you come back, I'll show you the answer. Okay, I'm going to assume that you've paused and worked this out. I'll step through this one. First of all, I've got my grid handmade here. It's going to be vertical because the larger of the 2 denominators is under the y term. So that's going to be a squared. And so that means a is 9, the square root of 81, in each direction. B squared is going to be 64, which means b is going to be 8 in each direction. Now all I have to do is connect them. That's it. I've drawn my ellipse. The example on the right, do the same thing. Hit the pause button. When you come back, I'll walk you through that one. Okay, again, I'm going to assume that you did that. Again, reminder, you can't apply any of these rules unless that's equal to 1. So divide it away. Once you do, you've got x squared over 25 plus y squared over 4 equals 1. That makes it a horizontal. This is the larger number. A squared is 25, a is 5, b squared is 4, b is 2. So there are the points 5 and -5, and the points 2 and -2. You connect them, and you've got your ellipse. Done. Now, finally, let's talk about foci. I keep putting it off, or focuses, as I call them. Well, I've just copied and pasted the rule here. C squared equals a squared minus b squared. C is the position of the focus, just as a is the position of the vertex, b is the position of the co-vertex, c is the position of the focus. Okay, so in the left example, that means c squared is equal to 9 squared minus 8 squared, or in other words, c squared is 17. That makes c the square root of 17, which is roughly 4. And there are, in those small green x's that I've made, those are the 2 focuses. That's where the 2 toothpicks would be in this diagram. Notice that the toothpicks, or the focuses, have to be along the longer of the 2 axes, the major axis. The major axis in the example on the right is horizontal. Again, c squared equals a squared minus b squared. Working that out, you're going to find that c is the square root of 21, and that's somewhere around 4.5. And there I've marked them off with green x's. Again, this time Those focuses are along the major axis, which happens to be horizontal in this case. Okay, the textbook then walks you through example 2. And I'm going to have to pick up the pace in order to finish this video lesson. They've given you 2 points, a vertex and a covertex. Well, the vertex is along the major axis. Notice it's the 7 is the y value, so that means this is going to be a vertical ellipse, and the covertex is -6. Well, if you want, you can plot those, and they're mirror points, and draw it, but what you've been asked to do is give the equation. Well, to do that, remind yourself what the general form of the equation is. X squared over one of the 2 measurements plus y squared over the other of the 2 measurements is equal to 1. X squared in this case belongs over b squared. So in that case, x squared is over 6 squared, or 36. Y squared is over 7 squared, over, in other words, 49. That's equal to 1, and that's your equation. How about this case, a little bit more challenging? They don't give you the vertex and covertex, they give you the vertex and the focus. Well, it's going to be horizontal because the vertex, the value is along the x-axis this time. And because that's true, and because the focus is also going to be along that line, you know that you've got this basic situation. You don't have that blue oval that's been drawn yet, but you do have the green and the red points from the information they've given you. Now, plug that into the generic form of the formula, and also remind yourself that c squared is equal to a squared minus b squared. Well, c squared in this case is 2 squared, or 4. A squared is -4 squared, or 16. So I've got 4 is equal to 16 minus b squared. Work it out, and you're going to find that b is equal to 2 root 3. Another way of saying that is that it's the square root of 12. Either way is fine. And so b squared is 12. So you now have a squared and b squared. A squared is 16, b squared is 12, and so your formula, here it is. X squared over 16, y squared over 12 equals 1. Now you're ready to try those two. Hit the pause button. When you come back, I'm going to show you the answers to both of those. Okay, I'm going to assume that you've paused and you've worked both of these out and are ready to see the answers. There are both answers. There are both equations. I only have time left in this video to do my best to try to wrap up the one on the right, so I'll work through that one fairly quickly. If you have questions about either of them, though, don't hesitate to come in and ask. Here's the one on the right worked out. First of all, realize, if I diagrammed this out, that my vertex, vertices would be at -7 and 7. My focuses would be along that same axis. Square root of 33, well, that's about 5.5. It's actually more than 5.5. So I've done the best I can in this small space with these red dots of illustrating where those toothpicks, those focuses would be. You apply that formula, c squared equals a squared minus b squared. You work that through, and you're going to find that b squared, well, negative b squared turns out to be -16. That means b squared is 16. Okay, well, wait a minute. Now I've got everything I need. B squared is 16, there it is. A squared is 7 squared, that's 49, there it is. I know it's supposed to be horizontal, so my larger term should be under the x term. And so this is how I derived this equation to fit those two pieces of information about an ellipse. That's it. That's the end of the video lesson. Don't hesitate to come in with questions. I'll look forward to seeing you in class.